Krishna Hari.
I am Matthew Duvall.
I'm Anurag.
I'm Samson.
Today we stand in front of you to talk about space elevators. And how many of you here use an elevator every day? Or think of life without an elevator. How would it be? And space elevator, from the name itself, tells you it's an elevator to the space. The main purpose of having it is that a space elevator is a proposed type of space transportation system. Its main components are ribbon rings of carbon, and it is designed to permit vehicles transportation along a cable to the space. And the main purpose of having it is that you can save a lot of money by using the space elevators instead of investing a lot of money on R&D for the rockets, and you save a lot on the fuel as well. And with the history.
Okay, I'm going to go over the origins of the idea and kind of like the history behind it I was able to find. The concept of it all could kind of almost be connected back to the Tower of Babylon if you really think about it in the Bible, because like they're trying to climb to the heavens. And well, that's kind of the same concept. The concept actually properly credited appeared in the 1895 by Konstantin Tsiolkovsky, and he proposed a freestanding tower that would go out into space. This idea would, of course, use compression to support the weight of the tower, which is normal where the support is at the bottom below the structure. And then in 1959, all concepts shifted to the tensile structures, and that's where the weight is supported from above. And that's kind of like a cool idea. And since 1959 and 1966, 4 American engineers renamed it like a skyhook kind of concept. They just kind of changed a little bit about it and named it skyhook. Discussed how the cable material would have to be twice the strength of any material known to mankind at the time. That was back in the 1960s, of course, so now we've kind of developed some material differently. We'll go over that later. But yeah, we need a material twice as strong as diamond to accomplish this. It's pretty intense. And in 1975, it was reinvented again with a new tapered cable design. And 1979, it was featured in a book called The Fountains of Paradise. In 1982, a book referred to it as a beanstalk. 93, Red Mars, the book, featured it. It's featured in a lot of books, basically, kind of as time progresses, because people kind of get interested with it. And then in 2008, after a book came out titled Leaving the Planet by Space Elevator, the Japanese kind of went forward with it, and they announced that they would build one, and they would price it at like $8 billion. And in 2011, Google revealed working on a space elevator on its Google X lab. And in 2012, Obayashi Corporation said that in 38 years, they could build one. It would hold 30 passengers. It would take 7.5 days to travel up there, but they don't have any cost estimates yet. And now we're going to go over to some concepts.
The construction of it is basically one end of the cable is fixed to the earth and the other end of the cable is fixed to the counterweight. So for the cable to stay firm, it basically works on the yo-yo concept, where the centrifugal force, when you rotate the yo-yo, it keeps the cable firm. So that's how it works. And the required length of the elevator is about 35,000 kilometers up into the air. And then we go on to the carbon nanotubes.
Right. So what's really important about this, and the reason it hasn't really been plausible until lately, is that this kind of strength you need in the cable that would be extended into space didn't really exist until very recently. And when it came into existence, what it ended up being was this thing called carbon nanotubes. What it is basically is it's these things constructed on the molecular level that they're just basically extremely strong, and they actually have the required strength and lightness that we would need to do it. And then how to power it. One of the main concepts that they've used is to have a solar panel on the bottom of the elevator, and then you shoot a concentrated beam or laser beam of solar energy at the solar panel, and that's how you could power it. Actually, as it continues to go up the cable, you need less and less of that power, because when it reaches the point of geosynchronous orbit, like where a satellite would just stay over the same place on the Earth, it'll no longer need to be powered by anything else. The actual outward, like it's sliding up the cable just because of the force that's taking it out, not necessarily anything pushing it up. So if we have the carbon nanotubes, and if we have this ability to power it, and we know how to get it up there, and it's so much more cost effective, you might be wondering why we haven't just started to build it yet. And there's a couple really fundamental problems. The first one is actually the carbon nanotubes. Now, the same things that make it possible for us to do it, it's actually making it impossible, because they are constructed on the molecular level. It's very hard to make much of it very quickly. It's kind of like the 3D printers, you know? I mean, you're doing little bits and pieces of it at a time. There's no real way to produce it quickly, and in the quantities you would need to make it very feasible. Yeah, the longest one that they've ever made actually is something like just under a foot long. So that's what makes it not very feasible. And also that counterweight that we mentioned earlier, you're talking about a planet-sized yo-yo. One of the things they've actually thought about trying to do, if you ever try to do this, they've theorized that you could maybe go and capture a passing asteroid that's coming nearby, which, you know, we've never done before. Or you'd have to send all this mass into space, which would kind of defeat the purpose of a more efficient form of travel, because to do it, you'd have to travel the conventional way several times. So those are pretty much the main reasons why we have not yet even started it, and can't for the foreseeable future, really. So, and yeah, now here's a really good video that we found explaining exactly what we were talking about with some more visuals.
You ever think about taking a vacation in orbit? Sounds ridiculous, right? Well, when the Space Needle here in Seattle was built in 1962, back at the dawn of the space age, lots of people thought they would soon be taking trips just like that. Of course, it hasn't quite worked out that way. It cost about $500 million just to take the space shuttle out for a spin. Kind of an expensive vacation, isn't it? One, please. Thank you. But what if there was another way to get to space? And what if that way were as easy and as cheap as riding an elevator? Well, strange as it sounds, some people think this kind of trip might just be possible one day, thanks to something known as the space elevator. A 22,000-mile long cable that we could ride straight to outer space.
What we're talking about is building the biggest thing ever.
And what enables this big idea is the discovery of something so small you can't even see it with the naked eye. A new material called a carbon nanotube. Fueled by the promise of these tiny tubes, people are already working to turn the space elevator into a reality.
It's basically a fairly straightforward system once you get down to the nuts and bolts of it.
First, launch a satellite to geosynchronous orbit, 22,000 miles above Earth. Then, lower a cable or ribbon and attach it to a platform at sea. Clamped to the ribbon, elevator cars or climbers could carry people and payloads up and down. Lasers on the ground would beam energy wirelessly to solar cells on the underside of the climber, powering electric motors for the 22,000-mile journey. Okay, I know what you must be thinking. A 22,000-mile elevator ride? These people are nuts. Like, what would even hold it up? Well, the idea is not quite as crazy as it sounds.
Imagine I have a yo-yo in my hand. As you spin the yo-yo around, the body of the yo-yo is thrust outward, and the string connecting you to the yo-yo is held taut. Well, this is the same principle that would keep the space elevator up. We're basically making a planet-sized yo-yo.
A space elevator could be safer and cheaper than rockets, giving routine access to the solar system. Bringing this far-out idea down to Earth, NASA recently funded a competition in New Mexico to build and race space elevator prototypes. It was held at the X Prize Cup, a carnival of cutting-edge space technology. in the tradition of competitions that stretch farther back than Charles Lindbergh's transatlantic flight. The aim is to inspire new advances in technology.
Wow.
This year, teams of students and weekend inventors are vying for the $150,000 in prizes in the Space Elevator Contest. The racetrack is a 50-meter ribbon suspended from a crane. Teams had to design and build climbers, then race them to the top of the ribbon. In place of the laser that might otherwise power a real space elevator, they could use only energy from the sun or beam from the ground. The best time wins, as long as you go faster than a meter per second. Bellerose and her team from the University of Michigan are next to jump on the ribbon.
The whole big idea behind doing this is to get engineers in school to start working on this. At the end of this event, there are kids here who are going to know more about space elevator technology than NASA scientists are.
Julie's climber is powered by a dozen spotlights that each have to track the solar panels all the way up the ribbon. The climber gets off to a good start. But the higher it rises, the harder it becomes to hit the solar panels with the spotlights to keep it going. After about 6 minutes of stopping and starting, the climber reaches the top.
We didn't make it in the time required, but one of the goals is to make it to the top, so we're very happy.
NASA's prize money is safe, at least until the contest resumes the next day. Now, if you think the whole idea of an elevator to space sounds like science fiction, you're right. It was popularized in the late 1970s in a sci-fi novel called The Fountains of Paradise by Arthur C. Clarke.
At last, we can build the space elevator, and then we will have a stairway to heaven, a bridge to the stars.
But as long as people have dreamed of building that bridge to the stars, no material existed to make a cable that's strong enough. That is, until we found that one of nature's most common atoms, carbon, was leading a secret life.
I wouldn't say carbon is promiscuous. I would just say it's very open-minded.
Carbon atoms just love to form extremely strong chemical bonds with one another. We knew they could be arranged in a lattice to form diamond, or in sheets to form graphite. But until recently, we had no idea they could also form tiny spheres called buckyballs, and tiny tubes called carbon nanotubes. Much stronger and lighter than steel, and able to conduct electricity, these cylinders of pure carbon have been called a wonder material, a new building block that might be used in everything from electronics to airplanes. But as a space elevator cable, carbon nanotubes have some big problems. The longest ones ever made are only a few centimeters, and joining them together end to end, one at a time, is simply not practical. So how would we ever use these tiny tubes to make a cable that's 22,000 miles long? Deep in the heart of Texas, scientists are taking a different approach to assembling carbon nanotubes.
It's the dream of the future, but it's an achievable dream.
To make a batch of carbon nanotubes, bake a silicon plate coated with iron particles at 1,300 degrees Fahrenheit in a special oven. Then add a dash of acetylene, a gas that contains carbon. When acetylene comes in contact with the iron, it releases its carbon atoms, which assemble, as seen here, into nanotubes. When the plate comes out, it's coated with a black soot that contains trillions of carbon nanotubes, all aligned vertically in what Ray Bachman calls a forest.
Think of a bamboo forest.
But unlike a real bamboo forest, the trees in a nanotube forest tend to stick together, thanks to a faint force operating at the nanoscale, called the van der Waals force. It's sort of like magnetism.
So when you pull one nanotube out, you pull its neighbors, and then they pull out their neighbors.
Pulling a whole row of nanotubes from the forest on the left, they can draw out a ribbon of pure carbon nanotubes, held together by nothing but the van der Waals force. This ribbon is less than 1,000th the thickness of a human hair, and it's stronger than steel. But can nanotube ribbons ever be made strong enough for a space elevator cable?
That is an unresolved question. But in science and technology, I've learned just never use the word never.
Back Back in New Mexico, the mood is more optimistic as the second day of the space elevator competition gets underway. Among those hoping to claim NASA's $150,000 prize is Brian Turner, captain of a truly homegrown team, the Kansas City Space Pirates. Hoping to make their elevator sail up the ribbon, the Space Pirates pull out their secret weapon, 15 mirrors, each the size of a twin bed.
Well, one person in each mirror.
Beaming sunlight to your collecting mirror,
Right.
to the solar panels,
Right.
giving the energy to climb.
Right. Are you ready? All right, here we go.
Halfway up the ribbon, the wind kicks in again.
Gotta get up there. I'm gonna go look at it this way.
Bouncing in the breeze, the parabolic mirror can't stay focused on the solar cells.
Come on.
The Pirate's elevator grinds to a halt.
Come on. If the wind hadn't been bucking, I might have been better off. But I can't believe I didn't make it to the top. I figured I could fight my way up there.
Next up, and favored to win, is the University of Saskatchewan Space Design Team, or USST for short.
Go time, right? It's go time.
Their secret weapon, a stationary mirror to reflect a spotlight straight up the ribbon to the solar array.
Go back a little bit. Okay, back to phase one.
It looks like they'd make it to the top in record time, fast enough to claim the $150,000 prize. So they win?
We have to have a little discussion about that.
Before the prize money can be awarded, the remaining teams get one last chance. But will we ever take a ride in a real space elevator?
I think it's crazy, but I still think it's possible. And I think it's something that if we can do it, we should do it.
Well, one thing's for sure. We've got a long way to go before that happens. But who knows? Perhaps someday technology will catch up with our imaginations and take the space elevator out of the realm of science fiction once and for all.
Yeah, just to kind of sum up where we're at right now with that, if you remember, they said their goal to win the prize money of like a substantial amount of money was 1 meter per second over 50 meters. So that would take, if they got that goal, 50 seconds to go 50 meters. And to give you some context, I ran track in high school and I could run 100 meters in sometimes close to 11 seconds, which to go 22,000 miles, you'd have to be going considerably faster. So that's it. Questions?
Yep.
Are there any questions?
Any questions? Here is a question. This is for recording, not for the sound.
Oh, okay. Is it any what do you call it, projections of like how long it would take to actually get to space from, from here to there?
7.5 days.
7.5.
With the proposed Japanese company, they said that they could build it in 38 years, and they approximated that it would cost $8 billion and take 7.5 days to get there.
So
For 30 people on one elevator.
Point A to B, where point A B, where the
So from like the station on Earth to the station up in space, it would take 7.5 days.
both ways?
Yep. Well, probably.
I don't know.
It's something. Yes. Another question.
We should also say that there was some we found conflicting evidences about how far out the space station would have to be. So that video said we think that video said that it needs to be at the point of geosynchronous orbit, and then a couple other sources we found said it needed to be just past geosynchronous orbit.
So the middle needed to be geosynchronous orbit.
Well, yeah, the point of balance
Yeah.
of the whole system, I think. So.
Any other questions?
The inhabitants of the elevator, the 30 of them, you said, so to speak, are they just sitting there for 7 days?
Probably.
I mean, I don't know, because people would probably go insane. So I would imagine if you wanted to make a profit at it as a company, you'd have to
have something to come.
Yeah.
Play Monopoly or something.
Any other questions? Now this, the rails, quote unquote, would be all the time standing in the air like this?
It's being pulled, not pushed.
Okay. Pulled
Okay.
from up.
Yeah, like this building is being pushed up by the ground. That would be pulled by the space station.
But the counterweight sitting in space would pull the line
I see.
out, so it wouldn't, there's no weight on it. It would just be pulled out.
And they accounted for the Earth revolving and motion and everything?
Yeah, well, that's what we were wondering about where you would place the station. Because I always assumed that you would put it at the point of geosynchronous orbit so that the line would stay straight.
Right.
But other sources said you wouldn't want to do that.
They accounted for wind or storms or something like that, no?
I guess it's not really an issue because this material is so strong. They never really mentioned it.
And if you think about how fast the Earth is going, that the force pulling it out must be so much greater than anything you could think of.
Okay.
But no, I didn't see any specific research on that.
Okay.
But I have thought about that.
Very good. Any other questions? So would you please join me in giving them a hand?